Hi guys, so this is the video for lesson 6. Most of us did it over a Zoom lesson, but this is in case you couldn't make the Zoom lesson. And we're going to be talking about proofs. But these proofs are going to be different from the ones that we did in the beginning of the year. The ones in the beginning of the year were 2-column proofs with statements and reasons, and we had a lot of writing, a lot of words going on, but we're not really going to do those like that anymore. Okay, we're going to focus more on numbers, and then we'll write a sentence or two at the end saying why the numbers and formulas we used are going to prove our point. So first we'll start with some background knowledge. So if you have a right triangle, okay, the only way a triangle could be a right triangle is if one of the angles is 90 degrees. So that's one thing that we could do. If we're trying to prove something's a right triangle, we need to prove that one of the angles is 90 degrees. And there's a couple different ways you can go about doing that. One of the ways that I'm going to do the most is by using slope. Because we learned in lesson 2 that if you have negative reciprocal slopes, that means that two segments or lines will be perpendicular. And as we've learned before, that perpendicular lines form right angles or 90-degree angles, which means we could have right triangles. So we're going to try and connect all of the things we know and make some proofs out of those and justify what we're saying. Another thing is about isosceles triangles. We know that isosceles triangles have two congruent sides and angles. We don't really know how to find the measure of angles at this point, but we do know how to find the length of sides. Finding the length of sides is really finding the distance between two of the endpoints, so we can use the distance formula like we did in lesson 5. So we're going to do some proofs using some of that, and we're going to do it first by making a plan, because if we have a plan, then it's going to help us figure out what formulas we're going to use so that we don't do too much work. And our plan is actually going to help us write our final statement at the end. So for this one, we are given 3 points, and you're going to graph them. And then we're going to prove that we have a right triangle. So we're going to start with our right triangle, and we're going to try and work that back into finding a way to plug points into a formula. Okay, so let's start with a right triangle. We know that all right triangles need a right angle. So by looking at our picture, we can tell that it's most likely going to be angle A that's going to be our right angle. So we're going to try and prove that angle A is going to be 90 degrees. Now, to tell something's 90 degrees, we're going to need perpendicular lines because perpendicular lines form right angles. So we're going to try and say that BA and AT are perpendicular because perpendicular lines form right angles, and if that means that angle A is a right angle, that means this whole triangle is going to be a right triangle. So that's where we're going. And the way we prove that sides are going to be perpendicular is by using the slope formula. Slope is the difference in the y's over the difference in the x's. So we're going to use BA and AT, and we'll do x1, y1, x2, y2 for BA, and then we'll do the same thing for AT, and you can do x1, y1, and x2, y2 for those 2 points, and plug them into the slope formula, and we'll compare them. When I do the slope formula, I'm going to put the sides that I'm using in the subscript, so that way we can tell which one is which to make it a little bit easier to compare. So this is my setup for these. For BA, we've got 1 minus 7 over 2 minus a negative 6, which is the same as adding 6. And then for AT, I put my negative points for point T, I made that my x1, y1. That way my negatives all canceled out here and I would have positive numbers. You can have these switched around a bit as long as your final answer is the same. So for BA, this became -6/8, and that reduces down to -3/4. And then the other one, we're going to have 4/3. As long as you have those answers, it doesn't matter how you got to them. Okay? You could have also looked at your graph and said, okay, the slope for AT, I know slope is rise over run. I can go up 4 and over 3, so that's 4/3. Okay, you can do that as well. So if you look at these two slopes, one of them is positive, one of them is negative, and the tops and bottoms are switched. Okay, so the top number here is the bottom number here, and the top number here is the bottom number here. Okay, the word for that, 2 words, is negative reciprocals. Okay, reciprocal means that you've flipped it so that the top and bottom have switched places, and it's a negative reciprocal because you've changed the sign. One of them's positive, one of them's negative. And we learned in lesson 2 that if you have slopes that are negative reciprocals, that means that they are perpendicular. So this is proving that this line and this line here are perpendicular, which means this has to be a 90-degree angle. And if that's a 90-degree angle, that automatically makes this triangle a right triangle. So we've done basically our plan, and we've kind of gone like this. We talked about the perpendicular lines, which made a right angle, which means it's a right triangle. So we're going to use that to write a sentence to summarize what we've just said. Okay, so the slopes of those two sides are negative reciprocals, meaning they form a right angle, and right triangles have right angles, so that means that triangle BAT is a right triangle. Now that's not all we can do with these formulas. It also says that we can use the distance formula to find the area of the triangle. Well, we've been able to find area before, but we've never been able to do it on a graph like this because we never knew the lengths of the sides. We know that area is half of the base times the height, and if we called this the base and this the height, and we knew those lengths, we could just plug that in. But in our picture here, we don't really know the length of these, but we could figure them out. We could figure them out using the distance formula. So we're going to use AT as the base and BA as the height, or you can swap them, it doesn't matter. As long as they're perpendicular, they're going to be the base and the height, and you can plug them in however you'd like. And we're going to plug those in. But we don't know BA and AT just by looking at it. We have to use the distance formula. So if you do that, you're going to get these as your answers. If you're not sure how to use the distance formula, go back to the lesson 5 video, and that's going to tell you how to do those more. So once you get 10 and 5, you can plug them in here. So we have half of 10 times 5, which is half of 50, which is 25. So 25 is the area of this triangle here. There are 25 full boxes inside this triangle. But you didn't have to count the boxes because we use the formula. All right, we're going to move on to example 2. Example 2 is telling us a whole bunch of stuff. So first, it tells us about these points, and then it says that we have A and B being the midpoints of 2 of the sides. So one way we can find the midpoints is by using the midpoint formula. Okay, so to find A and B, we do the midpoint formula, which is this. And when you graph it, it looks like that. Now, if you can see the midpoints just by looking at the graph, you can also just plot them that way because they're not part of our proof in the same way the other pieces are. So however you get to these points as your midpoints, then that's good. As long as it makes sense to you how you got it and you know that it's correct, then you're good to move on to the next part. This is asking us to do two things. First, we would like to prove that AB is parallel to XZ. So that's this line and this line. We're going to prove that they are parallel. And if we're trying to prove that they're parallel, we're going to compare the slopes. Going back to lesson 2, parallel lines have congruent slopes. They're going to be the same. So we're going to do the slope formula for AB and for XZ, and we're going to see that they're the same. And since they're the same, that means they're parallel. And we're going to write that in our final sentence. There's one more thing that they're asking us to prove here as well. We also need to prove that AB is half of XZ. Okay, so we're going to use the distance formula for that because that has to do with length. Whenever we see length, we're going to use distance. So we're going to say AB is half of XZ. So we're going to do the distance for both. And when you do that, you get AB to be the square root of 13 and XZ to be the square root of 52, which reduces down to 2 square root 15, or square root of 13, sorry. And you can tell by looking at that XZ is double AB, okay? Or you could also say that AB is half of XZ. Both of those are proving that this statement up here is correct. Okay, so we've done all of the math that we need to do, and we just have to bring it together in a sentence. So the sentences for these, I did one sentence for each thing that we proved. The first sentence is saying that the slopes of both AB and XZ are the same number. That means they have to be parallel because parallel lines have equal slopes. And then the second one is saying that the lengths of the two are, you can compare them, and one of them is double the other. So that's proving this statement right here. Okay, and when you explain, if you want to bring the numbers into your sentence, if that helps you prove your point, then bring them in. Okay, if it helps you explain it, definitely use it. The last question on here is talking about an isosceles triangle. And we know that isosceles triangles have two equal sides. So that means the length of two sides will be the same. And since we're talking about length, we're going to use the distance formula. If you're not sure which two sides to use, then do all three and use the distance formula for all of them and talk about the two that end up being the same. But if you're doing this and you can tell that two of them are the same, if you can tell that it's going to be these two, then go ahead and do those first. And if they end up being the same, then you don't even have to do the third one. So you're going to do the distance formula for both, and this is the setup that I used. You can have it be slightly different as long as your final answer is the same. Okay, it can be different depending on what your x1, y1, and x2, y2 end up being. And then your final answers, you could have either the square root of 50 or something that's equal to that. So if you put it in your calculator and you get a long decimal, that's fine, as long as you get the same long decimal for both of these. Okay? You could also split that into the square root of 25 and the square root of 2. But you're going to end up doing the exact same thing for this one. So as long as your two answers are the same, they don't have to be in simplest radical form. Okay? So save yourself the work, and as long as you've got them being the same number, you have proven that the two sides are equal. So you bring it together in a sentence that the length of both AT and RT are going to be the same number. So that means that the triangle is isosceles because isosceles triangles have two equal sides. Now, sometimes you can bring in more than one of these proofs together. So like your homework question, it says that you have a right isosceles triangle. You have to prove that it's both a right triangle and an isosceles triangle. So you're going to have to do a combination of example 3 and example 1. Okay? If our triangle looked like this, where you've got two sides being the same length and a right angle, you're going to have to do the slopes for those two sides, make sure they're negative reciprocals, and you're going to do the distance for both of those sides and prove that they're the same. If you have any questions about the proof part of this, make sure you let me know and I'll talk you through the proving part where you use the formulas to make these sentences. But if you have any trouble with these formulas, using slope and using distance, take a look at some of those other lessons earlier in the unit because those explain how to use those formulas in a little bit more detail. Okay? As always, you can contact me through email or Remind or Google Classroom. I'm going to try and get back to you guys as soon as I possibly can.